Okay, hello my people. I hope we're doing well. This is the second, um, second video on the review of parametric equations and their graphs. Um, when we uh, when we encounter something like this one, and we see it's x is equal to 2 plus tangent t and y is equal to 3 minus 2 secant t, what we need to recognize is the fact that this is also a conic section, and this winds up being a hyperbola. Now, let's go ahead and sort of plop it into our calculator. I mean, remember that we can do parametrics in there. You simply have to go to the mode and make sure you're in parametric. And then, of course, we can go back to y equals, and we can go ahead and put this pair of equations into x1 and y1. Now, of course, there's no button for secant, so you just have to construct that second term as 2 over cosine t. Now, let's go to the window, and let's see what it is that we're doing. Now, we need to go ahead and do it from 0 to 2 pi when it comes to t. And probably the x-min and the y-min is probably a little bit. Let's go to, and of course I'm benefiting from the fact that I already know what the graph looks like. Let's go ahead and -6 to 10, and then -6 to 10, and that'll give us something a little bit bigger. Now, notice that it did it in a very specific order, okay? It started right here. So let's go ahead and actually create some values, or a table of values. And the thing is that you can, remember, look at the table of values, but unfortunately for us, the table of values is not going to be populated by pi values, but it's going to be populated by integers. So let's go ahead and just plug in some values here. Now, when t is equal to 0, tangent t is 0, and this winds up being 2. Of course, when t is pi over 4, tangent of pi over 4 is 1, so this is 3. At pi over 2, cosine is 0. Now remember that both of these have an implied denominator of cosine, so both of these are going to be undefined at pi over 2. Now, at 3 pi over 4, this is going to be, tangent of 3 pi over 4 is going to be -1, so it's 2 minus 1, or 1. And at pi, it's back to 0, so it winds up being 2. Now, those are the easy values. The more difficult ones are the ones in between. And I won't keep you in suspense. This is 2.6, and this is roughly 3.7. Because, I mean, tangent of pi over 6 is, of course, sine of pi over 6 over cosine of pi over 6. Sine of pi over 6 is sine of pi over 6 is 1/2. Cosine of pi over 6 is √3 over 2, so it's 1 over √3, or √3 over 3, and that added to 2. But I mean, you can go through it, but let's just go ahead and skip ahead to the fun stuff. Now, on secant, it obviously is going to have integer values where cosine was either 1, 0, or either 1 or 1/2, or -1/2. At 0, obviously, is undefined. But at 0, secant is 1, so that's 3 minus 2, or 1. At pi over 3, cosine of pi over 3 is going to be 1/2, and therefore this is going to be 2 over 1/2, which is 4. 3 minus 4 is -1. And you can kind of logic that out the rest of the way, but this winds up being roughly 0.7, and this winds up being roughly 0.2, and this winds up being roughly 5.8 and 5.3. Again, when we get to 3 pi over 2, it's undefined, and of course at 2 pi, it's again going to be 2, 1, because you're going to start over. Let's go ahead and plot a couple of these. I know this is 2, 1 right here, and then it's going to be 2.6.7, and then it's going to be 3.2, and it's going to be 3.7, -1. Notice that as you emerge from 0 to pi over 2, you are getting this. You're starting here and you're going down and to the right, which is exactly the movement that we saw when we graphed it on the calculator. then it's undefined, and then all of a sudden, boom, on the other side, you get 0.37, right? It kind of does this, and then it starts up here and kind of is going to do the top part, and then it's going to finish out coming from the asymptote up to this original starting point right here. So we have 1, 5.8, and we have 1.4, 5.3, and we have 2, 5. Well, because you know that there's symmetry, you can sort of guess a couple more of these. It's going to be here, it's going to be here, and it's going to be here. And you know that, of course, this goes off along asymptotes, okay? Well, you see the fact that this is going to be the center, and basically you know that this is the major axis when you're graphing it that way. And so, you know, if you wanted to put in values, further values, you can, but it's going to kind of look like this. And that's going to be the graph. Now, when we eliminate the parameter, again, we have to be careful because we're going to be solving for tangent. So tangent t is equal to x over 2. And we're going to be solving for secant t, which is going to be y minus 3 over a negative 2. And we're going to be using the secant squared t minus tangent squared t is equal to 1. And remember that when you have a hyperbola, it is the positive, it's that positive term which designates sort of which way it opens, right? And so because the secant comes first, and it's going to be y minus 3 squared over 4, and this one is going to be, actually it's not x over 2, it's x minus 2, sorry, my bad. X minus 2 squared is equal to 1. That is an indication of why it opens up and down, right? The way that I used to talk about hyperbolas, because they're related, obviously, to the form of an ellipse, is a hyperbola is basically an ellipse that's sort of turned inside out. And if we were to, get it wrong and we were to accidentally, x minus 2 squared minus y minus 3 squared over 4 is equal to 1, that would have the same center, but it would be basically the hyperbola turned inside out in the horizontal direction, and that is not what our parametric equations are actually showing. Okay, so you need to be really careful. You can be less careful, obviously, with the sine and the cosine because it's addition commutative, but with the secant and the tangent, you have to be a little bit more careful. Okay. Let's go ahead and take a look at this set of parametric equations. We have x is equal to e to the 2t, and then y is equal to 2e to the t minus 1. Now, in terms of eliminating the parameter, this actually is going to wind up being relatively simple, but let's go ahead and plug in some values. Now, we know at 0, you're going to get e to the 0, so that's going to be 1. And here you're going to get 2 times 1 minus 1, or 1. Plug in 1, we're going to get e squared. And plug in 1 over here, and you're going to get 2 times e minus 1. Well, 2 times e is going to be roughly 5.4. Minus 1 is 4.4. By the way, this right here is 7.4. Now let's just go ahead and use the approximations from now on. Now, of course, when I plug in 2, this is going to be e to the 4th. Well, if e to the 3rd is 20, e to the 4th is way off the Cartesian plane, so I don't need it. So all of these are fine, they're just not on the Cartesian plane. Let's go ahead and plug in here. I know that if I plug in -1, I'm going to get not 1 over e, but 1 over e squared, and that's approximately 0.1. If I plug it in here, I'm going to get 2 over e minus 1, which actually winds up being a negative number. If I plug in -2, I'm going to get 1 over e to the 4th. That's going to be itty bitty, and it's basically going to get even closer. It's going to get even closer than that. So let's eliminate the parameter. I mean, obviously we don't have enough ordered pairs right here, and it's going to be really frustrating. But if we notice that if we notice that x is equal to e to the 2t, then I know that t is going to be equal to 1/2 natural log x, or natural log square root of x. Now, if I plug that in for, y is equal to 2 e to the t minus 1, I'm going to need to plug that in for t. Now, remember that e raised to the natural log of anything is that anything, okay? Because the exponential and the logarithm are going to cancel each other out. So 2 times e to the natural log of root x minus 1 is basically 2 root x minus 1. Okay, well that we know. We know how to deal with that one, okay? And we know that basically that starts here, okay, because it's the radical function stretched by 2 and brought down 1. And so, here, here, and then over 4 and not up 2, but up twice that, and then over 9 and not up 3, but twice that. And so it should look something like this. The question is, when is it at each point? Well, we know that at t is equal to 0, it's at 1, 1. And we know that at 1, it's at e squared 4.4. Well, e squared, as we said, is 7.4, so it's right about here at 7.5, and then up to 4.4. And that actually, pretty close to being right on the curve that I sketched, so I did it pretty accurately. But if we go the other way, we wind up getting 0.1 and negative 0.3, so we get that point right there. The question I have is, now this right here, we know that x has to be greater than or equal to 0. But, of course, we need to look at the original, right? Because the original always dictates. Here, in the elimination of the parameter, x has to be 0 or positive. But will x ever be 0? No. X has to be positive according to the form of this e. So actually what you get is it approaches but never actually arrives at that point right there as you go into the negative t values. It's almost like it emerges from close to but not at there from the negative direction, and then basically explodes out in that direction really, really fast. And so that the exponential doesn't dictate the shape, but it does dictate the pace at which those values are beginning to be ticked off as t becomes successively large integers. Because this is t is equal to 0, this is t is equal to 1, and remember, e to the 4th is somewhere about 50, okay? And 50 is, going to be rather large. So, and of course, that would be, if you were to plug 50 into here, or let's just ballpark it at 49, you're going to get 2 times 7, which is 14 minus 1. So it's probably going to be north of 13. Okay, so north of 50, north of 13 at t is equal to 2. Or, I tell you what, let's just go ahead and plug it into the calculator and see those values, because I think that's going to be instructive. Let's go ahead. I know that the x is e to the 2t, and this is 2 e to the t minus 1. Now, I don't really care about the graph. I want to look at the table of values. And, yeah, see, down here at 2, down here at 2, the readout is 54.598 and 13.778. And by the time you get to 3, x is over 400 and y is just shy of 40. So like I said, the exponentials in the parametrics don't impact the shape of the graph, but they do impact, exponentials accelerate really, really quickly, and what's accelerating is how fast the values are scooting along that curve as your values of t increase. All right, let's go ahead and look at another one. Okay, well that's all fun. Let's go ahead and take a look at some of the values. Let's go ahead and plug in. Well, first we know that we can't plug in -1, because if I plug in -1 here, I'm going to get a 0 in the denominator. I also can't plug in values less than -1, because then I'll get a negative in the radicand. So what happens here is we recognize that the domain restrictions, basically you would think that it'd be t is greater than or equal to, but it's just t is greater than -1. T has to be greater than -1. So we can kind of, ignore these values right here because they're going to give us errors when we try and plug them in. So let's start plugging in at 0. Plug in 0, I'm going to get 1 over 1. Plug in 1, I'm going to get 1 over root 2. Plug in 2, I'm going to get 1 over root 3. Plug in 3, I'm going to get 1 over root 4, or 1/2. Plug in 4, I'm going to get 1 over root 5. And then 1 over root 6, and then 1 over root 7. Now, if you notice, there's a pattern there. It starts at 1, and then as you get successively larger t values, this quantity is approaching 0 if t were taken off to infinity. Now, let's look at the y. I notice that the denominator is always 1 more than the numerator, and so this is going to be 0, and then 1/2, and then 2/3, and then 3/4, and then 4/5, and then 5/6, and then 6/7. Okay, well, you notice that those values, see, these values are approaching 0, these values are approaching 1. Now, they'll never get there, so 0, 1 has something to do with this graph. It's just going to be a hole, right? Because nothing ever gets there. I'm going to change the scale to -2.5, 2.5, so that each of the boxes is 1/4, or 4 boxes is equal to 1 unit. I think that's going to help us see things. At 0, 1, I'm going to have a hole. And then at 1, 0, I have a point on the graph. And then, of course, it's 1 over root 2. Well, 1 over root 2 is root 2 over 2, so it's 0.707. So 0.707, just shy of 3/4, 1/2. And then 1 over root 3 is root 3 over 3. And root 3 over 3, as we should know, is 1.732 divided by 3, so it's just shy of 0.6. So just shy of 0.6, and then 2/3. And then 1/2. And 3/4. And then, so basically, as you go from 0 to greater values of t, this is approaching that right there. Well, what about these values? Well, those values are basically all of the fractional values between 0 and -1. Remember, it can't be -1, but it can be all of the infinite number of fractional values between -1 and 0. And that actually is what happens here. And this actually goes on infinitely down like this. Okay, well, let's try to make sense out of that by eliminating the parameter. And I know that if I have x is equal to 1 over root t plus 1, that root t plus 1 is equal to 1 over x. And then if I square both sides, I get 1 over x squared. And I get t is equal to 1 over x squared minus 1, or 1 minus x squared over x squared. Okay, well, that was easy enough. We know that y is equal to t over t plus 1. We're going to take that and plug it into both places for t, and we're going to get y is equal to 1 over x squared over x squared over 1 minus x squared over x squared plus 1. Well, it's a complex fraction, so let's multiply by x squared over x squared. And what we're going to get is 1 minus x squared in the numerator, and then 1 minus x squared plus x squared in the denominator. I got news for you. Those x squareds in the denominator cancel, and I'm left with 1 minus x squared. Oh, well, that's just negative x squared plus 1, right? So that's just the parent function reflected over the x-axis and moved up 1. Well, that looks reasonable, but in order to capture the domain limitations based upon t's limitations, what I'm going to do is I'm going to have to say, for x is greater than 0. And that's going to have to go along with it because otherwise I communicate that it's the whole graph rather than just that section of it. Okay, and you're thinking to yourself, oh gosh, it's hard enough dealing with the elimination of the parameter and stuff like that without thinking about domain issues. Well, I mean, well, along with the power that comes with using parametrics comes the awful responsibility, right? Okay. Now, let's sort of work through some general equations based upon kind of what we know about parametrics thus far. Now, if I had 2 points, I would have the equation of a line, right? All I'd have to do is find the slope and then use one of the points. Well, how would that work with, I know how I can do that with point-slope formula and regular Cartesian rectangular equations. How would that work with parametrics? Well, when you're dealing with your x equation, you're not dealing with anything related to y. You're relating how x changes over time. Okay, so if I'm looking at x of t, I'm really worried about delta x times t. And then, of course, I have to have a starting point. Okay, well, let's use x1. And when I'm dealing with y, I'm just dealing with how y changes. And then I need a starting point for y, and I'm just going to use, the y1. And that's basically how it goes. And of course, the delta x can be rewritten as x2 minus x1, t plus x1. And the delta y can be y2 minus y1, t plus y1. Now, here's the thing. I could have used x2 and y2 for these two right here. It doesn't really matter. It could have, like I said, could have just as easily have been x of t is equal to x2 minus x1t plus x2, and y of t is equal to y2 minus y1t plus y2, and those would have both been legitimate ways to basically formulate parametric equations for 2 points and a line that connects them. And you're like, okay, well, that's really, really abstract and a whole lot of notation. Let's actually do something with numbers. Okay. So what we have here is this is your x1, y1. This is your x2, y2. And what we need to formulate is basically your x2 minus x1. So how about 5 minus 1, which is 4. And then plus, let's just use the x1. Plus 1. And then y2 minus y1, negative 2 minus 4, or negative 6t, and then plus 4. Or it could have just as easily, instead of 1, 4, could have just as easily used 5, negative 2, and it's 4t plus 5, and negative 6t minus 2. And both of those would have been legitimate ways, and of course you could have used any other point on the line to formulate those. Let's go ahead and move on to something, a tad more difficult. Let's just do ellipses in general, okay? Well, let's go ahead and we need to solve for cosine and sine. So x minus h over a is equal to cosine theta. And y minus k over b is equal to sine theta. And so what we have when we plug it into the sine squared plus cosine squared is equal to 1, or in this case it'll be cosine squared plus sine squared is equal to 1. But it doesn't really matter because addition is commutative. We will get that. And that, in general, is what it looks like, is what the equation of the ellipse looks like in rectangular form. And it came from what the equation of ellipse looks like in parametric. Okay, well, let's actually find the set of parametric equations for the following. Now, you can go ahead and plop them right into here if you can identify the h and the k and the a and the b. Well, h and the k is, of course, the center, right? So center at this one, if the vertices are plus or minus 5 at 0, then the center is at the origin. Now, you're wondering, okay, well, why in the world are the foci there? Well, remember, you not only need the length of the major axis, which is 2a, which will give you a, you also need the length of the minor axis, and that, of course, the half of the minor axis and the focal length, the length from the center to the focus, will create a Pythagorean relationship with this a value. And so what we have here is we recognize from here that a is equal to 5. And basically, if we have 5 as the hypotenuse and 4 as one of the legs, then b is obviously going to be equal to 3 because it's going to be a 3, 4, 5. Now, it is elongated along the x, so we know that the a goes underneath the x squared, and we have x squared over 25 plus y squared over 9 is equal to 1. Well, that's the rectangular equation. What we can do from here, of course, if we don't want to go straight from these pieces of information to this, which you can if you just don't want to memorize, and just remember that all we have to do is that. Turn them into squares and then set one of these equal to sine and one of them equal to cosine, and I get x is equal to 5 sine t and y is equal to 3 cosine t. Or, you know, it can be the other way around. It can be x is equal to 5 cosine t and y is equal to 3 sine t. Again, the only difference between these two, there's no difference in shape, there's just a difference in at what point you are at on the curve at any particular t value will be different, and of course the direction that the things are graphed in will certainly give you a different. There will be another difference, basically. Okay, and just for the sake of being thorough, let's go ahead and do that. Let's plug this set into x1, y1. So let's do 5 sine t and 3 cosine t. And then we'll do 5 cosine t and 3 sine t. Well, I'm going to go ahead and turn off this second one right here. And let's go ahead and let's zoom 6. Okay, notice where it started. It started up here at 0, 3 and spun around clockwise. Okay, if I go back to the original, I'll go back to the y equals and unhighlight the first one and highlight the second one, notice that it is exactly the same shape. It merely started over here at 5, 0 and spun it around counterclockwise. So like I said, it's the directionality and, you know, where are you at t is equal to 3 pi over 4 or whatever that winds up being the difference between them. Alrighty, let's go ahead and do for hyperbolas. Now, hyperbolas, obviously, we're going to be solving for secant and tangent, and that's x minus h over a is equal to secant theta. And so that basically means that it's going to be a hyperbola that opens up horizontally, because we know that the secant squared comes first in the difference, and since subtraction is not commutative, that's important. Y minus k over b is equal to tangent theta. And so this one's going to wind up being x minus h squared over a squared, and y minus k squared over b squared is equal to 1. And that would be it in rectangular form. Now, if we're given this information, now remember there is a Pythagorean relationship between a, b, and c for hyperbolas, but it is that focal length that provides the hypotenuse and not the length of a. And so if this is 5 and this is 3, then obviously it's going to be, again, a 3, 4, 5 right triangle. But this right here, since it opens up horizontally, right, we know it's going to look like that if you have a focus at positive or negative 4. This is our a value. Our a is equal to 4, the distance from the center to the vertex. Well, we've already basically spoiled the surprise. B is equal to 3, and of course the center is 0, 0, so h and k are 0, 0. Now you can go straight to this parametric, or you can go ahead and recognize that x squared over 16 minus y squared over 9 is going to be equal to 1. And of course, that transforms into x over 4 squared and y over 3 squared. But in this case, it does matter which one is designated as which, because you know that the secant squared has to come first, and therefore x is equal to 4 secant theta, or secant t, doesn't really matter, and y is equal to 3 tangent theta. And there you go. And there are a couple more problems on this in the exercises. I hope that this helps. We have one more video. We're going to run through a couple more examples just to kind of round us out and make sure that we are refreshed in our conceptual understanding of parametric equations before we start applying calculus to them. If you have any questions, as always, shoot me an email. Bye.